How's everybody doing out there? Well, hopefully everybody did a good job working with our addition rules for or problems and our complement problems for not problems. So now we're going to move on to our and problems. And so what we're trying to do is find the probability that some event and another event occurs. So one thing to kind of keep in mind and distinguish the difference between an and an or, other than the words and or problems, we were doing a single thing, like we were drawing a single card, we were rolling a single dice, and we were trying to see if one or the other occurred. So there was only one outcome, but we were trying to see if it fell into one of two categories. For and problems, we're going to be doing that thing as many times as we need problems. So if we're trying to find the probability of a king and a jack, so in that case we're drawing two cards for that. So we're going to be drawing a card for each and every probability that we're trying to find. We're going to be rolling a die for each and every probability that we're going to find. So for this one, we're going to have as many fractions as we need based on how many things we're actually trying to do. So if we're trying to draw 5 cards, we'll have 5 fractions. So these are all multiple event problems. So if we're talking about not problems, these are the ones where I mentioned where you're definitely going to have to use the rule of 1 minus. All right, so let's get in and take a look here real quick. So what we're going to do is we're going to flip a coin twice and then see what our outcome is. So for this one is just a reminder of our sample space for flipping a coin twice. So this is the one where we had heads first and then heads second, heads first and tails, tails, heads, and then finally tails, tails. So for this one, we want to say what's the probability that the first flip results in heads. So with this one, we're looking for which one where we had heads on the first flip. So it looks like we've got 2 of those. So we've got 2 out of 4. What's the probability that the second flip results in a tail? So in this case, we've got this one and this one. So it looks like we've got 2 out of 4. So what's the probability that the first flip results in a head and the second flip results in a tail? So if we were to look up above, the probability that we get heads on the first and then tails on the second, so we're going to get, 2 fourths times 2 fourths. Now when we multiply, we're going to multiply straight across the top, straight across the bottom. So we're going to get 4 out of 16, which if we simplify, is going to be the same thing as 1 out of 4. And if we notice up above, in our sample space, the only one that matches that criteria of the heads first and the tails second is going to be that 1 out of 4. So that's another way that we can kind of calculate these. Now we're not going to list the sample spaces for all of them because clearly those can be pretty big. Ultimately what we want to do is use our little multiplication rule, but we can see where these two things match up for these guys. All right, so let's take a look here at our another way that we can think about these guys. So using a little tree diagram. So if we're trying to draw 2 cards without replacement. So notice above, this was flipping coins. So our multiplication rule is going to be similar to our or rule in the fact that there's 2 scenarios that we're looking at. So we're either looking at with replacement or without replacement. So right now, if we're talking about without replacement, this means that, for example, if we took a card, we could throw it on the ground and we would just leave it there, and in the process it's going to reduce the size of the deck by 1, and it's going to also reduce possibly the card that we're interested in by 1. So to see what this would sort of look like from a tree diagram perspective, let's take a look here. So we're drawing 2 cards and basically just taking the first card, throwing it on the ground, and then reshuffling the deck, grabbing another card off the top, throwing it on the ground, and seeing what our probability would be that we get an ace the first time and then an ace the second time around. So this is looking like the probability of an ace and an ace. So that's ultimately what we're trying to figure out. And we're going to use a little Venn diagram to represent it. All right, so on our first draw, which is right here, this branch of the trees, so we obviously have two choices. We can either get an ace or we can not get an ace. And so the probability of getting an ace, since there's 4 of them, is going to be 4 out of 52. And then the probability of not getting an ace is all the other possible cards. So in this case, it would be 48 out of 52. So we're just taking 52 minus 4 to get that number. And now off of this branch, so now we've thrown one card, it's on the ground at the moment. So if we're reshuffling, and then we're trying to figure out what's the probability of the next draw. So on this branch, so I already got an ace on the first draw. So if I'm trying to figure out what the probability of getting an ace is on the second draw, well, since I got an ace the first time, there's an ace already laying on the table. So that means we've got only 3 aces left in the deck. And again, since we reduced the deck by 1, we've got 3 out of 51 possibilities for drawing that second ace. Now on the other hand, so I got an ace on the first draw, but I didn't necessarily get an ace the second time around. So that probability would be, so I've still got our 48 cards that are available, because I didn't draw an ace, because we drew an ace that first time, so all the other cards are available. But in this case, it's going to be out of 51 again, because we still have that first ace laying on the table. All right, so let's go down to the other branch. So for this one, we didn't draw an ace the first time. So if I'm trying to find the probability of getting an ace this time around, since we didn't get an ace the first time, all 4 aces are still there. But there is some random card laying on the table, so we still only have 51 cards available to us. But now if I go down here and do not ace and then not ace again, so in this case there was only 47 cards left over because I got a not ace the first time around. And then again, this is going to be out of 51 because there's still that one card laying on the table. All right, and so if I'm trying to find the probability that I got an ace both times, then what I want to do is I want to follow this part of the tree diagram. So the ace the first time and then the ace the second time. So what I'm looking at is that we're going to get 4 out of 52 times 3 out of 51. And then again, with multiplying, we're just going to multiply straight across the top, straight across the bottom. So 4 times 3 is 12. And then 52 times 51 is going to be 2,652. And so again, with these, I'm going to usually leave these as fractions just because sometimes these denominators can get so big that the probabilities can be fairly small. So I'm going to leave these in fraction form as well, just to make life a little bit easier. All right, so this is what we're looking at when we're trying to do these guys. We're trying to figure out whether the events are independent, which means that there's the first outcome is not going to affect the other outcome. So this is another way to think about with replacement. So in this case, so if we look, let's take a look and see if we can figure out whether events are independent or not independent based on what we have here. So for example, 3, a fair coin is tossed 2 times. The 2 events are heads on the first toss and then heads on the second toss. So are these events independent? So does the first event influence the fact the second one could be heads or tails? Since they're coins, just because I flip heads the first time, I'm not going to be less likely to flip heads the second time around. So this is an independent event. Oops, I should spell it right. All right, so these two things could happen, and they're not dependent on anything or anything like that. All right, so for B, the two events are it will rain tomorrow in Frederick, it will rain tomorrow in Thurmont. So technically, like even though Thurmont and Frederick are relatively close together, it could be raining in one place and not necessarily raining in the other. So the fact that it's raining in Frederick doesn't guarantee it's going to be raining in Thurmont. So these are not actually dependent events either. So these would also be independent. All right, for C, we draw a red card from the deck. We draw a second card without replacing the first card. So with this one, so we've drawn a red card, it's laying on the table. We're drawing a second card without doing anything extra to the deck. So that red card's on the table. So if we were trying to find the probability of a red, for example, we would have gotten 13 out of 52 the first time around. But the second time, we'd actually get 12 out of 51 because there's one less red card in the deck. So this is a dependent event. You draw a face card from the deck, then replace it and reshuffle the deck before drawing a second card. So the fact that we put the card back in means that we still had a 12 out of 52 chance of getting a face card the second time around as we did the first time around. So this is going to also be independent. All right, perfect. So let's take a look at our multiplication rule in general. So again, this is going to be for our independent events, or sometimes you'll see the word used without replacement if it's dealing with like cards or something like that. Or not without, with replacement, sorry. So with replacement. And so what we're doing, the probability of A and B occurring is just the probability of A times the probability of B. Or if we happen to have multiple events going on at the same time, so we can do the probability of A1 and A2 and dot, dot, dot. And again, we're just going to multiply each of those individual events together. All right, so let's have you guys work on practice 1 and practice 2 here real quick. So these should all be independent events that we're working with. And we'll come back in a little bit and talk about our dependent events and how we deal with those.